James Webb Space Telescope is identifying objects in the dark ages that, by best measurements we have, are large, fully developed galaxies. So who ordered that?
NASA's $10 billion James Webb Space Telescope has now been in space for little more than 2 years, but the stunning results it's already returned are proving it's worth every penny. Historically, our grandest views of deep space came from Hubble. But as of July 2022, James Webb takes us beyond what anything else has seen. From the faintest galaxies to the richest clusters, to mostly empty cosmic voids, to the deepest depths of far-off space and much, much more, the superior telescope has revealed details we've never seen before. Beyond all expectations, when James Webb focused on large regions of space that appeared blank to Hubble's eyes, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did stars go? How did they utterly go without a trace? Join us as we dig deeper into the shocking discovery made by James Webb, and how the disappearance of that many stars might affect our planet and our very future. First of all, you have to know that James Webb outperformed Hubble by more than we expected. When you look at the capabilities of James Webb and Hubble side by side, you would expect that our newest space telescope could do much more in less time. Whereas Hubble has a primary mirror that's 2.4 meters across, Webb's segmented mirror spans 6.5 meters. This leads to a resolution that's 270% as sharp for the same wavelength light, and light-gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages James Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see in the comparison of its composite image of galaxy cluster SMACS EO 723 with that of Hubble, is doing even better than that. Hubble time is divided up into orbits, as from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 9.6 hours or 576 minutes of Hubble time. But there's only a total of 3.4 hours or 203 minutes of Hubble data that's gone into these images, despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 12.5 hours and got 12.5 hours worth of data. What's the difference? Location. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere, in the way of its desired target, and can only acquire useful data when its target is in full, unobstructed view of the telescope. Meanwhile, James Webb is some 1.5 million kilometers away at the L2 Lagrange point. It always faces away from the sun, away from the Earth, and away from the moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency extends to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find the objects that appeared blank to Hubble's eyes in many cases, it can resolve them and examine their properties, whereas Hubble could not even see them at all. This helps us achieve one of James Webb's main science goals, to teach us in the goriest details possible how the universe around us grew up and came to be the way it is today. For instance, nearby, Jupiter appears as never before. Its bands, rings, aurorae, and moons appear alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging. Spectroscopically, transits detect absorbed light and transmitted light, revealing molecular presences. Star-forming nebulae display unprecedented details. From new, young blue stars to gaseous features, James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly. Now a 140-plus megapixel view, it expansively reveals far-flung galaxies. Just 1% of this view contains 1 to 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Arundel. But arguably, its greatest images are of individual galaxies. Webb's views reveal gas, dust, stars, and more. Central black hole containing cores shine in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either it's still there, still erupting its way through its death throes with less luminosity and perhaps obscured by dust, or it just up and collapsed into a black hole without going through a supernova stage. But in the worst-case scenario, the universe is just disappearing, and we're powerless to stop it. It's been nearly a century since scientists first theorized that the universe is expanding, and that the farther away a galaxy is from us, the faster it appears to recede. This isn't because galaxies are physically moving away from us, but rather because the universe is full of gravitationally bound objects, and the fabric of space that those objects reside in is expanding. But this picture, which held sway from the 1920s onward, has been recently revised. It's been only 20 years since we first realized that this expansion was speeding up, and that as time goes on, individual galaxies will appear to recede away from us faster and faster. In time, they'll become unreachable, even if we journey toward them at the speed of light. When you look out at a star, whose light arrives after traveling toward you for 100 years, you're seeing a star that's 100 light-years away, due to the fact that the speed of light is finite. But when you look out at a galaxy whose light arrives after traveling toward you for a journey of 100 million years, you're not looking at a galaxy that's 100 million light-years distant. Rather, you're seeing a galaxy that's significantly farther away than that. The reason for this is that on the largest scales, objects that aren't gravitationally bound together into galaxies, groups, or clusters, the universe is expanding. The longer it takes a photon to travel from a distant galaxy to your eyes, the greater the role of the universe's expansion, implying that the most distant galaxies are even farther away than the amount of time the light from them has been traveling. This shows up as a cosmic redshift. Since light is emitted with a particular energy, and hence a particular wavelength, we fully expect that it will arrive at its destination with a particular wavelength as well. If the fabric of the universe were neither expanding nor contracting, but rather were constant, that wavelength would be the same. But if the universe is expanding, the fabric of that space is stretching as shown in the video above, and hence the wavelength of that light becomes longer. The great redshifts we've observed for the most distant galaxies have absolutely verified this picture. But we can do much more than determine that the universe has expanded and continues to expand. We can use all the information we gather to conclude how the universe has expanded over its history, which in turn tells us what the universe is composed of. Once the light leaves a distant cosmic source, the expanding universe stretches the wavelength of that light. This leads to a redshift, where the more distant objects will have their light redshift for longer amounts of time, when different components of the universe were more important. By measuring sources at a whole slew of distances, discovering their redshift, and then either measuring their intrinsic versus apparent size or their intrinsic versus apparent brightness, we can reconstruct the entire expansion history of the universe. In addition, since the way the universe expands is determined by the various types of matter and energy present within it, we can learn what our universe is made out of. 68% dark energy, equivalent to a cosmological constant, 27% dark matter, 4.9% normal, protons, neutrons, and electrons, matter, 0.1% neutrinos and antineutrinos, about 0.08% photons, and absolutely nothing else, including no curvature, no cosmic strings, no domain walls, no cosmic textures, etc. Once we know the components of the universe to this degree of precision, we can simply apply this to the laws of gravity given by Einstein's general relativity and determine the future fate of our universe. What we discovered when we first applied this to the discovery of a dark energy-dominated universe was shocking. First off, it meant that all the galaxies that weren't already gravitationally bound to us would eventually disappear from view. They would speed away from us at an ever-increasing rate as the universe continued to expand and expand and expand, unchecked by gravitation or any other force. As time went on, a galaxy would get more distant, meaning that there was an increasing amount of space between that galaxy and ourselves. The galaxy appears to move away at greater and greater speeds due to the expansion of space. But this leads to an inevitable conclusion that is even more disturbing. It means that, at a particular key distance from us, due to the expansion of the fabric of space itself, a photon either leaving our galaxy toward a distant one or approaching ours from a distant galaxy will never reach us. The expansion rate of the universe is so great that distant galaxies become unreachable to our own, even if we were to move at the speed of light. At present, that distance is only about 18 billion light-years away, as the matter and radiation density is still dropping, and so is the overall expansion rate. If you consider that our observable universe is some 46 billion light-years in radius, and that all regions of space contain the same number of galaxies as one another, it means that only about 6% of the total number of galaxies in our universe are presently reachable by us, even if we left today and traveled at the speed of light. It also means that, on average, between 20 and 60,000 stars transition every second from being reachable to being unreachable. The light they emitted a second ago will someday reach us, but the light they emit this very second never will. It's a disturbing, sobering thought, but there's also a more optimistic way to view it. This is the universe, reminding us how precious every second is. It's the universe telling us that if we ever want to travel beyond our own local group, beyond the gravitationally bound set of objects made up of Andromeda, the Milky Way, and about 60 small satellite galaxies, that every moment we delay is another opportunity being lost. Of the estimated 2 trillion galaxies in our universe today, only about 6% of them are still reachable from the point of view of the Milky Way, and that number is getting smaller all the time. This also means that 94% of the galaxies in our observable universe are already out of humanity's reach, owing to the accelerated expansion of the universe caused by dark energy. Every galaxy beyond our local group, as time goes on, is destined for that same fate. Unless we develop the capacity for intergalactic travel and head out to other galaxy groups and clusters, humanity will forever be stuck in our local group. As time goes on, our ability to send or receive signals to what lies beyond in the great cosmic ocean will fade from view. The accelerated expansion of the universe is relentless. and the gravity we have isn't strong enough to overcome it. The universe is disappearing, and there's absolutely nothing we can do about it. At that time, one of the biggest existential questions we're capable of pondering is how it will all ultimately end. By observing the universe today, determining the laws that underlie it, and watching how the objects within it all appear to recede from us, we've figured out that not only is the universe expanding, but that the expansion is accelerating. As time goes on, distant objects outside of our own local group move away from us at eternally increasing speeds, eventually leading to a cold, dead, empty universe, powered by dark energy. Most of us assume, consistent with the observations, that dark energy is a constant in space, with its energy density remaining constant everywhere we look. But if dark energy strengthens with time, that would change our fate dramatically, leading to a scenario known as the Big Rip. If we want to understand what the Big Rip is, the first thing we need to understand is the motivation for considering it, the evidence for the existence of dark energy. If you imagine the universe as it was a long time ago, back in the earliest stages of the hot Big Bang, you'd find that there were two different effects vying for domination. There's the initial expansion rate, which works to drive everything apart as quickly as possible. And opposing it, there's the gravitational effects of all the matter and energy in the universe working to pull everything back together and recollapse the universe. Most of us would imagine three different possible fates, akin to the fable of Goldilocks and the Three Bears. Perhaps the expansion rate is too great for the matter and energy in the universe, where the expansion rate drops but never reaches zero, as distant objects continue to recede forever. Perhaps the expansion rate is too small, leading to the universe expanding to some maximum size, then contracting, recollapsing, and ending in a big crunch. Or perhaps the universe is just right, where the expansion rate and the gravitational effects of everything balance perfectly. One more atom and it would have recollapsed. But instead, we're just one atom away from that fate. But what we observe the universe to be doing is consistent with none of them. For the first few billion years, it appeared to be consistent with that perfectly balanced scenario. But then something strange occurred. If you had been watching any particular galaxy, you would have seen the effect of the expanding universe imprinted in that galaxy's light. From the time the light is emitted until the time the light is received, the expanding universe stretches that light's wavelength, causing it to be systematically shifted toward the red. The amount of redshift is related to the cumulative amount of expansion that has occurred and can be equated with an apparent recession velocity. Over time, if you were to measure that redshift for any object at all, you would have seen. It started out very large, decreased steadily over time, appearing like it was going to asymptote to zero, and then, all of a sudden, stopped decreasing after reaching some minimum value, and began slowly but steadily increasing once again, where it continues to increase, all the way to the present day. What's remarkable is that this effect cannot occur in a universe governed by general relativity if it only contains matter, both normal and dark, and radiation. Spatial curvature can't account for it either. In order to explain this observed phenomenon, some fundamentally new form of energy is required, what we call dark energy today. Perhaps the most popular, and certainly, by many metrics, the most compelling candidate explanation for dark energy is that it's simply a cosmological constant, a form of energy with a constant energy density everywhere that's found evenly all throughout space. If dark energy is either the cosmological constant from general relativity, the zero-point energy inherent to space from quantum field theory, or another type of field, akin to a scalar or pseudoscalar field that coupled equally to the universe at all locations and at all times, then it simply maintains a constant energy density and would cause all gravitationally unbound objects to accelerate away from one another at a constant rate, with their recession velocity increasing linearly with time. If this is an accurate description of dark energy, then the fate of our universe is known to some high level of precision. All of the structures which are currently gravitationally bound, like solar systems, galaxies, and groups clusters of galaxies, will remain gravitationally bound, with the largest bound structures never becoming bound to one another. Things will continue to expand, and the expansion will continue to accelerate until every transition that can possibly occur happens, and no further energy can be extracted from any physical process in the universe. But this doesn't have to be the case. Our best observations, from distant individual objects, from the large-scale structure of the universe, and from the temperature and polarization data from the cosmic microwave background, when they're all combined, teach us that dark energy is consistent with a cosmological constant to a precision of about 8%. However, it's still possible that dark energy is an evolving, dynamical quantity, but simply evolves in a fashion that's below the current observational threshold for detection. If dark energy does evolve, then it's possible that it will decay away entirely, returning us to that just right Goldilocks case. It will weaken and then reverse sign, leading our universe to contract in a big crunch after all. Or perhaps most fascinatingly, it could increase in strength over time, with its energy density rising as the universe continues to age. That final possibility, where dark energy strengthens over time, is the one that leads to a big rip, where structures that would otherwise be stable in the universe reach an inevitable point, where the expansion of the universe can eventually tear them all apart, each and every one. For many, many billions of years, the only difference between a universe with constant versus increasing dark energy will be in how the expansion rate changes, how severely the light from distant objects gets redshifted. With constant dark energy, the redshift increases linearly with time, whereas with increasing dark energy, the redshift increases at a greater than linear rate with time. This increase, if it occurs without any cap or limit on it, will eventually start to affect these large bound structures in a rather unpleasant way. First, the largest, most extended galaxy clusters will start to dissociate as the outer galaxies become unbound from the cluster as a whole, hurled off into intergalactic space. Next, the closer, more compact portions of clusters and eventually galaxy groups get ripped apart as well, until all we have left are individual galaxies. Afterwards, the individual galaxies will have their dark matter, gas, and eventually stars ripped out of them from the outside in. The outskirts of the galaxies are stripped away first, but eventually even the cores of galaxies are stripped down to their individual star systems. Then, close to the end, individual solar systems are torn apart. The icy bodies of the Oort cloud are stripped away, followed by the Kuiper belt objects, then the outer planets, the asteroid belts, and even the inner planets. Finally, the individual structure, like planets and moons, are ripped apart into their constituent components. In the penultimate instance of the universe, molecules are torn apart into their individual atoms, electrons are stripped off of their nuclei, and atomic nuclei are ripped apart into protons and neutrons, which are then ripped apart into quarks and gluons, just moments before the fabric of space and time itself is demolished by dark energy. Although this might sound like a far-fetched scenario, you must remember that if dark energy strengthens over time, and you have no restriction on the amount of time that can pass, then all of these occurrences are simply inevitable. The only question is when. Fortunately, dependent on the nature of dark energy and how its strength changes over time, we can calculate how long it will be before each step occurs. When it was originally proposed, that first step could have occurred as soon as 22 billion years from now, but that's been pushed out to some 60-80 billion years from now, at minimum. However, once that first step occurs, tearing apart structures on scales of about 20 million light-years, everything else proceeds rather quickly. Dark energy needs to strengthen tremendously to start overcoming the immense force of gravity. And once it can do so for the most loosely bound structures, we're talking only hundreds of millions of years before all of the galaxies are torn out of their home groups and clusters. Then it's only tens of millions of years until stars are ripped out of their individual galaxies. Next, it's only a few months until the outer planets are ripped away from their parent stars, and weeks before the inner planets suffer the same fate. It's only in those final few minutes that our planet itself will be torn apart, and fractions of a second for molecules, atoms, and more to be ripped apart. The greater the amount of force and energy is required to tear something apart, the less time there is remaining until the universe itself comes to an end. After all, the Big Rip is one possibility for how the universe could end. But if dark energy increases with time, we have to face the facts. At some point, we're going to have to deal with energies and temperatures that are high enough that we've never explored them. In those regimes, anything that's not ruled out remains possible. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.